All right, so Thursday, 9:27. Our learning objective is perform operations with polynomials using Pascal's triangle for binomial, and use Pascal's triangle for binomial expansion. Okay, so you have your answers to your homework. This you would have had to copy down, but look, it's right in front of you. These are some of these special patterns that we've talked about a little bit, but I would like to go over more. When you have the, I guess they're calling it sum and difference. Okay, because it's a product pattern, so then it's difference of perfect squares. They're showing when you square a binomial, the patterns that it looks like with examples, and then, of course, what it looks like to times out a plus b times a plus b times a plus b. Okay, and that's kind of the pattern that you've got going on there. And there actually is a cool pattern. We're going to learn how to expand things with bigger numbers than 3. So, going on to the next 2 slides of the presentation. Pascal's triangle. So there was this wonderful French mathematician, Blaise Pascal. Of course, I don't know how to say his name, but anyways, he was playing around with numbers one day, or he also noticed that other people had found this array of numbers, and he was like, what if I write these numbers in a certain way? So Pascal's triangle is an array of numbers, and it can be used for many things. So he started off, okay, I'm going to start with the top, starting with the number 1. Each beginning number and ending number will also be 1. And he puts 3, makes it look like a triangle, right? Okay, so you got 1, 1, 1. For the next row, which is going to have 3 numbers, okay, kind of like a pyramid. Okay, you're going to have 3 numbers. First is 1, last is 1. And then in between, we take the sum of the 2 uppers. So 1 plus 1 gives me 2. Again, 1 and 1. These 2 added gives me 3. These 2 added gives me 3. Okay, so you see where we're kind of going. Continuing on, 1, 4, 6, 4, 1, 1, 5, 10, 10, and 5, and 1. And honestly, you can keep going on forever. We're going to stop here, though. And so he said, he made this arrangement of numbers, and he's like, what else can I do? Well, he decided to label each kind of level as separate rows. The first one. So he decided to name each of these levels or rows. So you have your the very first one he calls the 0th row. I don't know, because nothing's really happening here. There are other reasons for the names of the rows, and you'll kind of get first, second, third, fourth, fifth. I mean, it's pretty easy to remember, right? 1 has 2 1s. The second row has a 2 in it. The third row has 2 3s. The fourth row has 2 4s. The fifth row has 2 5s. Right, so you can kind of get an idea in your head of what your next level will look like. So we're going to use, so this array of numbers is actually used in so many different things, but we're going to use it for something called binomial expansion. So if I were to take a binomial and times it by itself, we already know the pattern that we get from that, right? We have a squared plus 2ab plus b squared. Well, there are patterns, then we can do the cubic, okay? I guess there's a pattern for that one. But is there a pattern for a plus b to the fourth? Like, do we seriously have to put a plus b times a plus b times a plus b times a plus b? That sounds exhausting. Okay, so Pascal noticed that these numbers actually showed up in other places in math, and we're going to use them to expand a binomial. And you know what? I decided I'm going to change this example. We're going to do x plus y to the power of 5. So yours will probably have the right number. I'll print out yours to have the right number. So x plus y to the 5th. Okay. We can actually use Pascal's triangle to help us out with this. The first thing to know is that whatever's happening with the x's and the y's, we know what needs to be times by the coefficient, or what needs to be the coefficient. So we look to this number. That's the row in Pascal's triangle that we look at. So the 5th row in Pascal's triangle is 1, 5, 10, 10, 5, 1. Those will be my coefficients, or at least times by my coefficients. So 1, 5, 10. I'm definitely going to run out of room here. And then we'll do 10, 5, 1, because I'm going to kind of run out of room. If we follow the pattern here, we'll notice that a is to the power of 2, since that's the first variable. Here, the powers of a and b add up to 2, and here b is to the power of 2. So I could actually call this b to the power of 0 and a to the power of 0. So you could see that the powers always add up to be this number. 2 plus 0 is 2. 1 plus 1 is 2. 0 plus 2 is 2. And obviously the b to the 0 and the a to the 0 are just 1, so they're not written and they don't need to be. That's the pattern we're going to follow for our x and our y. So 1 is going to be times by the first term. It needs to be x to the power of 5 and y to the power of whatever adds to 5 and gets 5, so 0. X to the power of 5 and y to the power of 0. 5 plus 0 is 5. Good. X descends 1 each term. Y ascends 1 each term. So now this x will be to the power of 4, and this y will be to the power of 1. 4 plus 1 is 5. This x should be to the power of 3. This y should be to the power of 2. X should be to the power of 2. Y to the power of 3. This x will be to the power of 1. Y to the power of 4. This one will be x to the power of 0. Y to the power of 5. My exponents do add up to give me 5 each time. And I have no numbers in front of the x or the y that need to be times by 1, 5, and 10. I left spaces because sometimes you have a minus in here that will change some of your signs. This is plus, so all of our coefficients will be plus. So you have your coefficients from Pascal's triangle. You have your pattern of descending and ascending exponents. You're done expanding. All you have to do is just clean it up, okay? Such as y to the 0, you can just write. You don't need to write it. We don't need the parentheses. So for our final answer, we get x to the power of 5 plus 5x to the 4th y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 xy to the 4th plus y to the 5th power. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Your final answer won't always be the same as the row you used in Pascal's triangle. But x and y did not have a coefficient, so it is the same. It is 1, 5, 10, 10, 5, 1. And that's your final answer. 3x minus 1 to the power of 4. All right, we're going to use Pascal's triangle to expand this one again. So the numbers that should be times to the coefficients would be the numbers from the 4th row of Pascal's triangle. So we take a look at the 4th row, and we have 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Lots of space, okay? The worst thing you can do, in my opinion, with binomial expansion is just crowd it and then lose track of where your signs are and your numbers and not be able to read your own handwriting. All right. So x and y were our first and our second terms in the binomial. So what needs to happen is that this first term needs to go to the power of 4, and the second term needs to go to the power of 0, because 0 plus 4 is 4, just like we did in the last example. (3x) should be to the power of 4. (-1) should be to the power of 0. 4 plus 0 is 4. Now remember, when we had it as just x and y, we just had x and y, okay? So it looks a lot more scary because we got more things going on, but again, it's just the first term and the second term. One needs to go, but the exponents of those two terms will always add up to the exponent here. Continuing on. 3x will now go to the power of 3, and (-1) will go to the power of 1. 3x to the power of 2, (-1) to the power of 2. 3x to the power of 1, (-1) to the power of 3. And then 3x to the power of 0 and (-1) to the power of 4. Now, do you see why I don't put signs in between? Because this (-1) is going to make every other sign negative. So let's clean it up. 4 is the power for 3 and for x. So this should be 3 to the 4th. In fact, if you don't mind, I'm just going to write out what that actually is, the number version of it. So 1 times 81 times 1, right? (-1 to the 0 is 1. So my very first term is 81 times x to the 4th. Sorry, I was trying to times all the numbers first, and then we have x to the 4th as well. All right. This (-1 to the power of 1 makes this sign negative. And now I'm going to cross it off just because I took care of that negative. Now I have 3x is to the power of 3. So I have 4 times 3 to the power of 3 is 27 x cubed. Maybe I'm going through too many steps at once. So let's write that out. Let's write this 3 to the 4th times x to the 4th. And then we'll write this one too, and I'll bring this down. So 3 to the power of 3 and x to the power of 3. All right, so we had already said that this negative 1 to the power of 1 is negative 1. So it's going to make my result for this negative just because there are no negatives inside of here. 4 times 27 is 108. Then we have 3 to the power. Okay, checking this negative 1 to the power of 2. That becomes positive 1. So now I have a plus here. This should be 6 times 3 squared, which is 9. And then x should also be squared. 54 x squared. Continuing on, negative 1 to the power of 3. Since it's an odd power, that leaves it negative. And then dropping it down, 4 times 3 times x. Now that this is to the power of 1, we're getting to the easy part. 12 times x. Negative to the power of an even. That's a positive. 3. All of this to the power of 0 is 1, so 1 times 1 times 1 is 1. And that is how we expand Pascal's triangle, and our pattern for binomial expansion can help us, instead of having to do the box thing a billion times, we can follow this pattern to expand binomials with Pascal's triangle. There's actually a link to another presentation from a former student of mine, Sean the Pro, who actually went over Pascal's triangle for his essay and shows how you can use it in binomial expansion as well.